This is the fourth and last module in the chapter on the electric field, and it concerns the torque and the potential energy of a dipole in an electric field. Well, in the last module, we defined a dipole as having as being two charges, a minus charge Q and a plus charge Q, that are separated from their centers a distance d. And we define that dipole as a vector, which is the positive charge times the distance between them. Now, such an object as this, if it is in the presence of an electric field, let's imagine now we have an electric field going along here, and you can see what would happen if that electric field is there. There are two things that are going to happen. The first thing is this electric field is going to push on the positive charge in this direction and push on the negative charge in the opposite direction. So it has a tendency to want to turn this around, and therefore it will exert a torque. If the electric field were in this direction, you can see that torque is maximal, because the electric field would force upward here and downward here, and what would that be? Well, it would be the distance out times the force, which would be d over 2 times q times that force of the electric field. But, so the torque would be, for the perpendicular force, the torque would be what? Remember, it's r cross f. So in that particular case, it'd be the distance out, which would be d over 2, times the force, and the force is going to be what? It's going to be q times the electric field. But there are two of those pushing on it. It's what we call a couple. Remember that from angular momentum. So we have twice as much. So you can see that this is a 2 cancels a 2, twice as much as one from one side and one from the other. And each one has a half of a distance out. That's r cross f perpendicular. That's the f perpendicular. It's going to be q times e. So here's the f perpendicular, and here's the distance, d over 2, and I have two of them. So we can see that the torque is going to be equal to d times q times e. And this is the e that is in the perpendicular direction to the dipole. Well, this is the dipole. This is the distance times the charge. So it's p times e perpendicular. And therefore, it's easy to see that if that's e, p times e perpendicular, then that's exactly with torque, p cross e. So the torque is given by p cross e. And what emerges here is, of course, the fact that this e perpendicular is e times the sine of theta. So this is magnitude of p, magnitude of e, times the sine of the angle between them. Now this is the part you remember when we discussed torque in that earlier module on angular motion. This is e in the perpendicular direction. Let's kind of go back and look at how that arises, okay? It would arise up here in this diagram. Remember, the dipole is going to be pointing this way from the negative to the positive charge. The electric field is going up this way. And so we have an angle between those, and that angle is theta. And if we look at that, what we want is the amount of this force, or this electric field right here, that's in the perpendicular direction, not aligned along r, but perpendicular. Well, the perpendicular part of this vector here, if we say, what is this part right here? This is p times the sine of the angle between them, where this is theta. This is theta. I've written it twice here. This is theta. Then the part pushing upward will be the perpendicular part. So therefore we do have p times e times the sine of the angle between them. And that gives us our torque. Okay, how would we work a problem like that? Well, it's very simple. If we have a dipole here, let's just go back to the beginning. Maybe we have 4 coulombs here and a minus 4 coulombs here. And it's separated by a distance of 2 meters. What is P? P is going to be the dipole moment. the dipole moment is going to be 4, the positive charge times 2 meters, right here. So P is going to be equal to 4 times 2, which is 8. Okay, now imagine we have that, and we have an electric field that's going in this direction at an angle theta. Maybe this electric field, maybe the electric field has a magnitude of 7, and the angle theta is 20 degrees between the two. Then the torque that's going to be exerted on this dipole is going to be what? The torque is going to be P, which is 8, times E, the magnitude of E is 7, times the sine of 20 degrees. And you can easily work that out and see what that torque is going to be. Again, another question that would come up in this is, do you know the direction of that torque? Well, remember that this is going to put a force like this up in this direction, force down here in this direction. So it's going to try to turn that dipole just like this. Well, if you think about the right-hand rule, where the thumb, where you wrap your fingers, your hand around the axis, your thumb is, if your fingers go in the direction of the torque, then in the direction of the motion or the turning, like for a water pipe or anything, your thumb would point straight up. So this particular case that I've drawn here would have a torque facing out of the page towards your face. This would be out of the page towards your face. So the vector nature is out of the paper. The final thing here is how much energy does it have? And you'll notice that there's an equation here, U is equal to P dot E, and the energy, or the potential energy, is P dot E rather than P cross E. And this potential energy should be written as U. And remember, torque is a vector because it's a cross product of two vectors, and that gives you a vector. But the dot product of two vectors gives you a scalar, and energy is a scalar. And this tells us that the energy that a dipole has in an electric field is P times E times the cosine of the angle between them. Now, the way that is normally done is you can see that if P and E are perpendicular, then you get the cosine. If P were to go this way and E goes this way, say P is here and E is this way, then P dot E, since they're perpendicular, this is 90 degrees. And the cosine, this is P times E times the cosine of theta. And the cosine is 0 here. So in this particular case, the energy for U is equal to 0. And as this is bent more in this direction, it's greater, until finally you get E times P times the cosine of 0, and that would be 1. So in that particular case, where E is this way and P is this way, then we say U is going to be, well, what's the angle between them? The angle between them is 0. The cosine of 0 is 1, so this energy is P times E. Now what if they're in the opposite direction? If they're in the opposite direction, then E is going this way, but P is going this way. And if P is going this way, then E dot P is going to be what? It's magnitude of P, magnitude of E, times the cosine of the angle, but the angle now is 180 degrees, and that gives us a minus 1. So we can see the energy here, if they're in opposite directions, is minus P times E. If they're perpendicular, it's 0. And if they're in the same direction, it's P times E. So I've given 3 cases here. And of course, if you know the angle, then you just write P, like we did here. U in this case would be 8, which is P. E, and what did we say the electric field was? 7. In this case above. And then if the angle were, say, 20 degrees, this would be the cosine of 20 degrees, and that would give the energy. And so this is very useful for finding how much energy is stored by having a whole bunch of dipoles in an electric field. And if those dipoles are perpendicular, it's zero. But the lowest energy state, you'll notice, is not where they're perpendicular, but when they're pointed in opposite directions. Why is that? Well, the electric field is going this way. P goes this way. That means the positive charge is here, the negative charge is here, and therefore this can't orient itself in any way that would be of lower energy. So it wants to go exactly in this direction. And that gives us a calculation for how we calculate the energy and how can we calculate the torque and the concepts behind those.